So good morning. So yes, the objective of this talk will be to present an overview of fracture mechanics that is quite a challenging task in 1 hour, 1 hour and a half. So I will provide a biased overview. We'll talk a bit about fracture mechanics, the basic concept in quasi-static. Probably Jay will tell you more about dynamic fracture tomorrow. And to progressively move to the fracture of disordered material, and in particular to avalanche dynamics in fracture problems. That is one of the main focus of this program. Pierre, if you find a pointer, je reviens si tu me retrouves. Si tu en as quelque part. Okay, so what is the main objective when we work on fracture problem? The main objective is to derive a theory that is predictive in order to avoid, in particular, in order to predict and avoid failure. But there is also other aspect that in some system you want to trigger fracture, or at least you want to manipulate fracture properties of materials. So I would say on a broader perspective, fracture mechanics deals with predicting fracture and also designing fracture, how to manipulate and control fracture properties of material. And when you talk about material design, material control, we will see that heterogeneity of material, disorder of material will play a key role. So we want to have a theory that takes into account also material microstructure. All right, but let's progress in a development of a predictive theory of fracture. And the first naive question we will ask is how to predict the strength of a brittle solid. And here, to start with, I borrow an idea from Jay and Mike Marder that consists in taking a simplest model possible of material, an homogeneous elastic solid made of spring that's going to describe your atomic bonds, and you want to make a prediction from it on your critical stress at failure. Then you just going to take a failure criterion based on deformation of spring and say that your material will break when spring are deformed over a length that is a typical distance between atoms, interatomic distance. And so then you get the stiffness of your spring from the elastic modulus of your material, from the Young modulus, and you get a failure stress that is typically of the order of the Young modulus. Maybe the Young modulus over 5 if you make more elaborated calculation on when two atoms get separated from each other, don't interact anymore from each other. And this prediction is actually quite bad, of about, if you take typical materials, of about two orders of magnitude. You predict strength that is much larger that the actual strength of material. Strengths are weaker.
So the failure
occurs much before. Yeah. This is a kind of theoretical strength that is hardly achieved, that can be achieved in some kind of ideal situation, flawless material, but it's not at all the general case. And to go a step further in the understanding of fracture, you need to introduce defect. That will be key in the process of fracture. So you introduce this kind of elliptical cavity in your solid, and then since you have an elastic material, you can calculate stress field in this system as you apply a tensile stress on the side of your sample, and show that you have stress concentration, stress amplification, and the amplification factor is 1 over the square root of your curvature of your local radius of curvature at point A. So you you can, from it, you clearly see that the actual stress that the material will undergo is much higher than the stress you apply on the side, and you start to understand why the strength of material is actually weaker than the theoretical, lower than the theoretical strength. Okay, then you have, so you see there is a high dependency to defect, and you want to, but you want to have a model. You want to somehow develop a model that is not such dependent of defect, and ultimately such defect will lead to the most catastrophic defect you can imagine in your system, a slit crack, because then the radius of curvature goes to 0, the amplification is maximum. So nature is not is made this way. You always end up to have the worst defect possible in your system. So from this type of model, you can also calculate stress field and show that at the tip of near the tip of this crack, the stress is provided by this k over square root of r singularity. R is the distance to the tip. K is called the stress intensity factor. Tells you how much your external stress is amplified at the tip. K is proportional to the external stress. But if you keep this model and maintain, yes.
Where does this cross over to sigma external at which scale?
Crossover from where to where? From the previous transparent?
Yeah, can you go back one?
Yeah.
Yeah, so, right, so at which row will this be?
Okay, rho tends to 0. This is the stress in A.
Yeah, no, but when rho becomes bigger, at some point I have to recover sigma external, no?
Yeah.
So at which
I don't know if you recover sigma external.
Let me comment. My students always ask me this question when they start in the business or something, so I even have an answer. Okay, this is an asymptotic expansion, so you're looking at the nastiest component of the stress field. You have, this is just the first term in this expansion, but it's the only singular term in the expansion. So all of and this, it turns out, as Laurent will show us, is universal. But all the non-universal parts of the stress field, you just add them to it. But as you get near the stress field, this thing dominates. So you can explain all of fracture mechanics just by the existence of the singularity. Obviously, for R that goes to large scales, then this goes away, and the other components and the other terms become dominant. So you'll recover the external stress that you're applying.
Okay.
But at the scale of A, or
No. Let's say that if you move from A to a distance that is of the order radius of curvature, you recover the stress. Okay. Yeah, I'm looking really at the tip. But that's it. The length scale you talk about is provided here by O. Then to come to the point of J.
The prefactor?
Which prefactor?
Sigma E.
There is a length scale missing that is actually the length of this cavity in this direction. Square root of. On the next is very different because you cannot to go from this one to the next. Since I'm consider only the stress field in A, I need to go. Rho tends to 0. I have an infinite stress in A. That is consistent with the result here. At the tip, I have R equals 0. I have an infinite stress. That doesn't tell me so much.
So okay. What's the difference between this model and the previous model?
The infinite is 0 curvature.
Oh, and that's finite curvature.
Finite curvature,
okay.
Yeah, exactly.
Rho is like microscopic then here, right?
Yeah, somehow this model is not completely irrelevant. You have in any physical problem, you will have a length scale, at least the atomic scale, or you will see later, you will always have a regularization of this singularity through a material length scale. That's not completely irrelevant. Okay, not going to comment too much on that, but if you plug typical radius of curvature, you can measure maybe on crack. You can have, okay, you don't want to go, but you can somehow rationalize a bit the factor, the 2 decades you see of difference between these quantities. But okay, let's move on. So if you maintain a stress-based criterion with this kind of approach, you see since stress field is diverging, you will have actually no resistance to fracture somehow. If I apply just a little stress here, I will have infinite stress here. So I have no reason for the crack to stop growing. It's kind of a naive vision, but with this model, using stress-based criterion, you will have systematically failure. So it's also not the correct approach, and actually a powerful way to look at the problem is to consider energy transfer, energy balance. When you have a crack in your system, and that is going to move over some length, over some incremental length delta A. Then instead of looking at stress field, so I'm going to look at energy variation. And during this propagation, I have the work of the external force that is going to balance the variation of elastic energy in the system, in the solid, that is under some stress, and a variation in surface energy, or if you want, an increase in terms of dissipation, because you propagate a crack, or you create new surfaces. This costs you some energy, but I noted delta ES. And the idea to look at this problem is not to look at energy variation, but rate of energy dissipated, of rate of energy released. To look at rate, you're going to gather these 2 terms that correspond to the mechanical energy of your system, and you're going to look at the variation of this term normalized by the surface of propagation, delta A times B. Okay, it's a rate of variation of mechanical energy as your crack propagates over some unit surface. Same thing for the dissipation. Instead of looking at delta ES, I'm going to normalize it by the surface over which the crack moved, and I'm going to have a rate of energy dissipated to make the crack propagate over some unit surface. So I have my relevant quantities, fracture energy, elastic energy release rate. That will be the one we use all the way to in the remainder of the talk. You already feel that this is a thermodynamical driving force. Energy you gain as the crack move on, and this is a resistance to crack growth, fracture energy.
So I missed what A dot B is?
Delta is incremental advance of the crack, and B is a kind of normalization factor over the surface area. What from this if you have a crack propagation, if you have crack advance, then your energy balance is satisfied, and so you have G equal GC. This is what is written here. If you have propagation, you necessarily have G equal GC. If no G is smaller than GC, then you feel that the crack cannot propagate. You have your thermodynamical driving force lower than your rate of dissipation you need to plug in your system to make the crack propagate. You have stable crack. So this is the concept of Griffith's criterion or fracture mechanics is telling you if a crack is stable or not, more or less.
It's a little, I mean, the one comment I have about this is when one talks about the surface energy, one is not talking about a sharp mathematical surface. One basically has a region where elasticity works. It breaks down on small scales. You're saying, I know how to calculate the elastic energy from the large scales. So everything at the small scales that's hard, I'm calling surface. And so the crack may move across and it may disrupt a volume that's micrometers on either side from the crack's face, but that's all thrown into the surface.
Did I mention predicting the stability of brittle cracks somehow? You have this approach can fail if you have, as you say, inductive failure if you have dissipation in the volume.
But as long as it's confined to 10 micrometers or something
it's fine.
quite big compared to atoms, it still works, right?
Yeah, but in ductile failure you have a growing,
it's the whole volume.
It's the whole volume and it fails. But that's a good point, and we come to that. So we have put here all our trouble. We have put it in this term, and we're going to, as you do fracture problem, you're going to open the box each time you look at fracture problem. What is inside this term? What do you call dissipation? Here we assume that we can, we actually, practically speaking, we can measure it on different materials, have a value of fracture energy tables, but no explanation, obviously, from this type of approach, continuum mechanics approach. You cannot have any insight on the value of GC. And you assume that is a rate as function of, is a constant as function of, it's a constant that depends only on the surface that is broken.
Excuse me, why do you call this dissipation this right hand ferrule? I mean, if it's just creating the surface that could regain the energy.
Yeah, no, that somehow will be, if we will have a real surface energy, you would say, okay, I break the bond, and later on I can bring back together and recover this energy. Practically speaking, you don't recover this energy because it's not only bond breaking, it's a lot of dissipative processes during fracture. I don't come through the detail, but you cannot heal in 99% of the case a crack. So the actual energy is lost. And also, if you compare this term to the actual surface energy, it can be, okay, recently there has this measurement, this beautiful measurement that show that in a perfect crystal silicon, you can have GC actually equal to the surface energy. But this is the exception. The general case is several times to several decades time more, several tens of times larger than the surface energy.
For metals, it's 300 times, and for polymers, it's 3,000.
Yeah,
and it's really a good approximation that these plasticity and dissipative processes sort of scale as the surface area of the...
Not in ductile failure, for example. I think
as long as this delta A, as long as you're looking at crack propagation over lengths that's much longer than the width of the region above or below that's involved in the non-elastic plastic deformation, then this works. It's basically, you've taken, again, you've said, okay, there's this little region that's my black box, and I know how much energy is going into it because I can calculate the elastic energy. That's straightforward. And I'm just going to treat what's going on in there in terms of this energy.
I guess that makes sense. I just want to ask a precise question, which do you also need to make the assumption that sort of the amount of plasticity or the amount of dissipation is proportional to the surface area for the surface term, or if it's like fractal or something, would it break down then? That's the question I'm asking.
I don't know about fractal.
It has to be proportional
to
delta A. It has to be proportional to the distance moved.
So
any fractal has to be confined
to something that you can approximate as a surface area term.
Okay, you can also measure this term as function of crack length. You can have complex effect where this term increase. If you have non-stationary process zone, if you have non-stationary dissipation, this term can increase as a crack. Okay, I don't want to go to complication, but consider it's a material property. So far, it works pretty well.
But at this level, also, we're just talking about conservation of energy. There's nothing fancy. Next step, you're going to do a bit. Then you're going to start to assume that you have a singular field, like Laurent mentioned, and how that, because conservation of energy we all learned in kindergarten or something like that. But now in first grade, we have to now look at how this is conserved and all that, and that's what fracture mechanics is. So it's assuming a singularity at the crack tip. Now, when that breaks down, which could in very plastic materials, suppose material deforms at scales where you don't have the square root singularity, then it's a tough material. It's a material that you use to build bridges and whatever, steels and stuff. A brittle material is one that allows the singularity to develop. And then you can use this asymptotic expansion to calculate all of this stuff trivially, not really trivially, it's tough, but it can be done.
But you can do it even for the tougher things. All that's different is in one case you have a really wide region that's plastic, and in the other it's really small. So
but to push this forward, you still need this assumption that the singularity exists, that's the dominant term in the stress field.
Okay, there is one, let's go to the end of the discussion. There is one case where all this collapse is when you lose this small-scale yielding assumption, meaning that this zone where dissipation takes place has to be small with respect to the sample size. So at least you have a zone somewhere in your sample where elasticity works. There is one assumption for this to work correctly.
Just a quick question. So when you say fracture energy, it is the energy required to make the fractures?
Yes.
Okay. And you were just trying to say that if the energy required to make the fracture is greater than the energy released due to the fracture, then it don't fracture anymore.
Yeah, if you don't provide a rate of energy due to your mechanical loading large enough for making the crack propagate to create this new surface, this does not propagate. The crack does not propagate yet.
And so it should be greater than equal to GC, right? In the second condition.
Okay, if you provide more energy than the fracture energy, then like Jay talked, you can use this energy in kinetic energy, or you can make the crack, making the crack grow faster, and the system will dissipate another way the additional energy. So to make a link with the previous slides and the singularity, the driving force we derive here is provided by, you can show that it's provided by this formula. It follows, it's scaled as k squared, where k is the stress intensity factor. So you remember in the previous slide, the stress field at the tip is singular. There is a constant characterizing this singularity. And the larger this constant, the larger the driving force for the crack, and you have this relationship. Okay. So this approach is extremely powerful. Has been used to design planes, boats, and is used on a regular basis. The drawback that we started to discuss is it's limited to homogeneous media. It doesn't give you any hint on the GC, on the dissipation. If you now want to illustrate here how heterogeneity, how macrostructure can be relevant in this problem, let's consider this kind of idealized case where we have two phases, a crack propagating in a material with some heterogeneity, some toughness heterogeneity, or some elastic property heterogeneity. And the singularity at the crack tip is going to make this problem very, very difficult. And in particular, it's going to make the response of the fracture response of the whole system very sensible to what's going on at the crack tip. We saw previously that the crack response is mainly governed by the prefactor K of the singularity, but it's also governed by the value of the resistance GC at the tip. So anyway, with this singularity, we have brittle fracture is a propagation of a singularity in your medium. You have an extra sensibility of all the local properties, and you have a huge effect of local property to overall behavior. So it's going to that's the reason why fracture is going to be a complex multi-scale problem. It's not going to be very simple to go from small scale to large scale. You will have a huge effect of local property at the large scale, but it's also an interesting opportunity to design, because it means that with well-designed heterogeneity or macrostructure put at the correct length scale, you can manipulate fracture properties. That's also an opportunity here for material design. So now let's go more into the actual description of fracture and crack propagation within heterogeneous materials. So I'm going to consider heterogeneity only in fracture energy and focus on that. So in a medium where I have a homogeneous fracture energy, the crack is straight, driving force is constant along the crack. And as soon as I introduce some heterogeneity, I'm going to deform the crack front, and I'm going to have a driving force that might depend on the front position. So I want to rationalize this effect, and I'm going to introduce now a field of fracture energy, meaning that the resistance may vary with the position you consider in your material, and it's going to write as a constant average fracture energy plus some perturbation that depend on the location you consider in your material, and the key point is going to be what is the value of the local driving force in some point as function of the geometry. So I'm going to address this problem in a specific case. Slow crack propagation, weakly heterogeneous material, this is important. So in that case, I have small out-of-plane perturbation that I'm going to be able to, so I will be able to neglect them at first order, and very large sample. Under this specific condition, you can have an analytical expression for the driving force in some point as function of the geometry of your front. This is the expression. You calculate this through development of the stress field using perturbed boundary condition, and it writes as a constant term plus a perturbation. That is a non-local perturbation, telling you that the value of the driving force here depend on the geometry of the full geometry of the front, and also just we have a minus f here, telling you that if the front is late, the driving force is slightly larger than the average driving force Gx, and if the front is in advance, the driving force is slightly smaller. So that's why I call a line elasticity, a pseudo-line elasticity. The distribution of driving force along the front try to maintain the front straight, okay? And this non-local term, one more comment, arise from the fact that if you have perturbation here, but maybe we see it better on the next game. If you have a perturbation here, it perturbates the stress field in a whole area around the perturbation, so you have effect on the long range.
So basically, my understanding is that the integral part is really the line tension part.
Yeah.
You try to stretch it flat, right? That's all.
That's it. It's a specific kind of light tension if you have a sinusoidal perturbation of the front, the restoring force is in 1 over the wavelength, while if you had a local classical surface tension line, you will have 1 over a wavelength to the square. Okay, then you have your driving force in this problem, you have your resistance. Then you can assume you need a kinetic law, telling how the crack is going, what is the velocity of the crack in some point. It's a local propagation law as function of your driving force and your resistance. So the simplest propagation law you can think of is the proportionality. Actually, you can show that it is also the law you expect from dynamical fractal mechanics, but under some specific condition. It's also a practical law. It's over dynamics. So you for many reasons you're going to pick up this kinetic law that actually makes a rather good job, as we will see in the following.
But just it's also somehow consistent with the equation above, because the line tension is calculated assuming that the entire stress field is able to equilibrate before the contact line moves.
Mm-hmm.
Right? I mean, it's effectively a quasi-static limit. The elastic energy, and so if you have something that's inertial, it actually is less likely to satisfy that condition too.
This works well under very slow loading or certain material.
Okay.
It actually works well under slow loading, but when the crack is moving at the speeds of information in the material, because this equation of motion, a crack has, in theory, no inertia. It's like a massless particle. So it'll immediately, this df dt is just the velocity, the instantaneous velocity of the crack at every point z at every t. And you might think, yeah, this is a static, a quasi-static approximation, but under the right conditions, and if you're really interested, we could go into a long discussion of what the right conditions are, but basically a crack will instantaneously, at least in this theory, adapt to whatever the driving is at the point. Now, why is it massless? It's basically because the information propagates away from the crack faster than the crack can move. It's limited by the wave speeds of the material, so it never can interact with itself if it's a large enough medium.
But the equation for G is assuming an instantaneous propagator.
Yeah. It's
So
a quasi-static.
that part's problematic.
This is a static.
It's a static calculation.
That's true.
It's
But
the
the
part
equation
below
of
you're
motion.
But the absence of inertial term has solid background also. It's not only an assumption that we need over the dynamics. The absence of inertia is really inherent to crack problems. Yeah.
So just naive question. I don't really understand. What is M?
What is, sorry?
M.
Okay, it's a point along it's a point on the front. It's just
Why isn't it just given by
really to
f of z of t? I mean, I don't understand. So f of z comma t is the completely specifies
okay, so
the crack location of the crack.
I want to insist that it's a local propagation law that you apply at every point along your front. And let's consider this point. Then I'm
along the crack, you mean?
Along the crack, along this orange line, yes. And at this specific point, I can predict the velocity, the local velocity of the crack. That is going to move forward if G is larger than GC. It's actually the discussion we had a bit before. And actually, this is not completely correct. If G is smaller than GC, you have zero velocity. Is the Griffith criterion applied locally in every point?
But I'm saying, I'm sorry.
About this term,
I can think of G as a functional of f of z.
Yeah.
So is this is just notational? Is my understanding?
Yeah. Sure. Let me.
So that's really G of.
Let me gather the term above, and then maybe it's going to simplify things. That's true. G is a functional of f.
And it just depends.
It depends on f only. So f I didn't mention the in-plane perturbation of the front. I assume very small out-of-plane perturbation, weakly heterogeneous material, so I neglect the effect of out-of-plane excursion of the front. The stress field, then you plug you apply your local fracture energy on the front you are considering, and the complexity in your equation arise from this nonlinearity. Okay. If you didn't have that, you have a linear equation you can solve in f, but because of the presence of f of your unknown inside the heterogeneous term, you get into big trouble. Okay, in most of experiment, we don't impose the load. We don't impose force or stress. We generally impose displacement. So that's not such a big difference. If you impose, for example, an opening velocity, you can show that the term that were there, gx minus average gc, actually is going to simplify into this term. In other words, imposing a velocity here is going to impose you a velocity of the front through a geometrical factor. Both are proportional, and you will have an effective driving that is a rigid bar moving at velocity Vm, that is the average crack velocity, pulling on your elastic line with some spring of constant k. And k, we can calculate it, depend on the geometry of your sample. So this gives you an effective driving through springs, and also from this equation you get the spatiotemporal evolution of your front, but you get also the driving if you pull at constant velocity, you don't impose the force at which you pull on your sample, you predict it. And you predict it using this formula that is the distance from the position of the rigid bar pulling on the line to the average position of the line. It's also, if you plug that into that, you realize that the effective resistance of your solid is the average of this term over Z. So my point here is that, yes?
You can continue.
Yeah, I finish. So my main point here that the front geometry tells you what is the resistance of your material. Simply because the front deforming pick up some local properties that are going to set you what is the macroscopic property. So determining front geometry is key in this problem.
So I see in your equation, mu doesn't depend on Z. Is that a really good approximation, or do you worry about that?
Actually, we should ask specialists of event dynamics. Whatever term you take, okay, we take homogeneous term, but this value of mu doesn't change many things in the. So mu we take it constant, and in some and on a large range of value doesn't affect the result. What you finally obtain is G equals GC along the front, as much as you can. Sometimes G equals GC.
So what you're saying is the time scale doesn't really matter anyway. So
it's it's a good point. It's setting a time scale, but it's setting the time scale at which you move from one metastable state to another. It's going to.
Final if you are quasi-static, the final metastable state does not depend on mu.
Yes.
So that's why it's sort of okay that it doesn't depend on Z, because you don't really care about it.
Yeah, actually we can, if we believe in that the elastodynamic theory works, you can calculate this mu, and it's related to the velocity of speed in your velocity of sound in your material. But when you look at this value, it doesn't seem very reasonable. So, from experimental point of view, so it's kind of effective mobility. It's not so clear right now, but we are lucky it doesn't affect so much the results.
So this field of fracture energy, does it evolve with time, or is it fixed all the time?
No, this is the assumption of brittle failure. You have really in 2D a point singularity moving in a medium that is frozen, and in 3D you have a line of a very thin line moving through a 3D medium that is frozen also.
So you're saying that GC stays constant?
Yeah, it's a quench noise. Yeah.
Okay.
You definitely have more complex situations when your material can evolve, but I will focus on this case right now, on brittle failure.
Just a short comment. I hope you don't mind.
Sure.
This is perfectly correct as long as the crack is slow, so it can equilibrate with the boundaries, for example. That way, the velocity is dependent on how hard how fast you're displacing the material, because the crack knows about it, because the sound, the time scale is the sound speed, to go back and forth in the boundaries. Things can get pretty hellish though if the material is overstressed, for example. If you're not locally conserving energy, but you initially put in more energy than the sample can deal with. So what does it do? The crack will start to accelerate. It'll accelerate, and then this mu stops being trivial and starts to become actually a singular function of the crack velocity. So as long as it's if you're putting in energy at the same rate it's being dissipated, and you're always making sure that that everything is kosher at the crack front, and then this whole this doesn't look so trivial to me, but it's still it's relatively simple. I'll show you examples maybe tomorrow when the crack starts to move like a bat out of hell, or starts to approach its asymptotic velocity, which is the sound speed, and then things become funny.
So if you pre-stress it or something, do something like that.
We talk. Yeah, an example. We talk about the singular. Okay, if you start from from this problem, for example. If you load this sample, since you don't have stress singularity, you have to load it a lot before the crack actually starts. And when the crack starts, you have a lot of energy in your system that make the crack accelerate.
Yeah, but that elastic equation is implicitly assuming that you're minimizing the energy subject to the boundary condition of the crack.
Yeah.
And that's only a valid approximation to the state in the limit where it's quasi-static.
Yeah, so the
as soon as
crack
you go away
knows
from that,
what
that
you're
whole
doing
thing-
everywhere.
Can you estimate mu?
No.
Only measure.
You can calculate. It's assuming that the
It's 10.
singular field. So
It's 10 to the minus 3 about, because it's average GC over the velocity of sound. So it would be 10 to the minus 3 about. But it's a kind of, okay, can be discussed. If you have some dissipative process, I think, not sure this value is applying on the general case. All right. So to investigate this equation, to investigate the prediction of this equation, and there is an experimental system that is actually simpler than the 3D fracture problem. The difficulty with this is the transparency. How do you observe crack, 3D crack in material, and how do you control heterogeneities in this system? Well, now with new techniques, 3D printing, you can start to deal with these problems. But this system is somehow simpler. The crack is confined to a plane. It's a peeling of an adhesive from a heterogeneous substrate. You can look directly at the front shape, and you can pattern the surface with heterogeneities. Okay. Also, does it make sense from a physics point of view? Yes. It's not so different from the crack problem. You can also derive an equation of evolution. The same idea arrives here. The same idea arises that the mechanical energy you input in your system by the work of the external force is used to peel your system. So you have a transfer of mechanical towards adhesion energy or fracture energy. And you can also consider perturbation of your front and the perturbation and the pseudo-elasticity of your line is the same type. It's of the same type than the crack front problem. The only difference is the factor 4. Here you have an elasticity of your line that is 4 times larger than the crack front elasticity. So you will have amplitude of your deformation 4 times smaller. But that's not a big price to pay. And then the applied driving force has a different expression as function of the geometry of your system and loading. Instead of being proportional to the square of the applied force, it's not linear to the force. And there is a dependency to the peeling angle, but that's not also a big problem. So the first application to somehow compare the model with some experimental observation is to consider perturbation, toughness field or fracture energy invariant in the propagation direction. Then I get rid of all the complexity I talked about previously. I don't have the unknown geometry of the front inside the heterogeneous term, and I can solve analytically the solution. What do I have if I impose GC independent of X and depending on Z only? I have a stationary front shape that I can predict and I can compare with experiments. So I have two examples. The first one is if you introduce one defect of larger fracture energy in the middle of your sample, you have propagation this way. So at this point, the crack is late, and you can measure the perturbation, the black dot. Compare with the theory. Here in this system, we control defect toughness. We print defect with a well-known value of fracture energy, so we can really test quantitatively the prediction of the model. Here is a different example. Is another example. We introduce a periodic array of obstacles. Here are sticky lines, sticky defect, and here is a front with black dots. Is the front shape in this part where it propagates further. Okay, can be explained by the theory. We can also do finite element.
In the elastic term, I'm confused why the thickness of the adhesive and the substrate didn't enter.
Okay.
Shouldn't that be a cutoff on the kernel?
Yeah. But that's a good point. You have actually it's a different source of here where the dominant elastic. Okay, you have the driving force here that inputs some energy of your system. You have stored energy, elastic deformation energy stored in your system in bending energy. You see these wrinkles here. They are the ones storing the energy. These are the ones that cost you energy to deform more here than here.
So the substrate is rigid.
Substrate is rigid. You have a wrinkling elastic plate, and you can use bending theory to calculate the excess of energy you need to pay in deformation to deform it like that and calculate driving force. Actually, each time, since you normalize by GX, each time there is no extra edge dependency over. Okay, actually we cannot have edge dependency. Is the limit edge tends to 0. It's a thin plate theory model. So perturbation you consider are necessarily larger than the thin plate. That's what we use, the thin plate thickness.
I have a question regarding the general formulation. If you look at this type of approach, you see it in dislocation dynamics. You have almost exactly the same thinking.
Yeah.
And then in the fluid, viscous fluid front propagation, Taylor problem, you have same equation.
Yeah, sure.
So what is really unique here in the crack? Is the crack a fluid front, or is it a dislocation line, or just a generic question for line motion?
Yeah, because you talk about pseudo-line elasticity. You don't have so much choice. As long as you have a system, behind this non-local term, you have an argument of Dogen that tells you that if you have a system where if you modify your interface over some length scale lambda, you have an influence in the bulk over a length scale lambda, the same length scale here and here, you will always end up with this kind of non-local kernel. So the only difference we can have is the prefactor. What you have in this is so the amplitude of the elastic term. You have also different in cutoff. I don't talk about cutoff. We started to discuss. If you have perturbation of the order of the thickness, this doesn't work anymore. And if you have cutoff, if you have perturbation of the order of this bending length, radius of curvature, you have also other effects. So the difference are in the cutoff, in the amplitude of the terms, but not in the non-local term.
So this 4 is non-local.
From the plate theory, you actually, we can go into. No, you can actually 4 is nothing really universal. If you go to smaller angle, you will have effect of stretching, and then this prefactor is going to depend on your peeling angle. So there is nothing really magic. As long as the peeling angle is larger than some critical peeling angle, you get 4, but it can change with the peeling angle at small peeling angle.
And so the shape is supposed to be a logarithm as you move away. The next slide.
Yeah, that's it. Here it's a logarithm. Right there. Here there is not a simple form you can write. Okay. Before moving to disorder, if I have time, moving to disorder system. Now you have a model that can be predictive, both for the shape of your front and for predicting the force. I didn't discuss it, but you can predict force using the model. You can use it for design. And this has the idea of this system where you want to have a response of a peeling response that is different when you peel your system one way or the other. So then you can, what can you do? You can use a model to find shape that makes the peeling asymmetric, and what you find is that this moon shape type of peeling site make a good job. The idea the idea behind is what we discussed, is that the front shape select local property. And so if the front shape is different, if the front deformation is different as you go this way or this way, the force will be also different. And then it's a game to finding which shape is doing the better job as having different resistance in both directions. So here, experimental front as you go this way. Here are the calculated shape. And here are also the force, pinning force that you get by integrating GC along your line here in this way and here in this way. So here the mechanism is just that the front get trapped along a line that is very thin and feel a lot of tough material. While here, when it attacks the defect in the other way, you feel a very thin line that it can cross by staying almost straight, as we can see here. Just at the very end, it feels some kind of tough material. So that's just an illustration how you can use defect heterogeneity to control up to some limit the resistance of the effective resistance of your material. All right, so now let's second part of the talk. I wanted to discuss about crack propagation in heterogeneous media. So I'm sure for many of you, they recognize the equation of evolution of the front is the one of interface with long-range elasticity that give rise to depinning transition if the heterogeneous term is the disorder, is a stochastic quench noise. So this was the idea, I think, of the experiment designed by Malloy in Oslo to make propagate a crack through an interface with random spatial distribution of defect. And how this is done, they use 2 plates of plexiglass. They sandblast one of the plates, stick them together, and make the crack propagate. At the interface, they measure the crack front position using fast camera. They record it at some high frequency, and you see an avalanche-like dynamics. This typical size is a few centimeters, and the movie is accelerating. I think it's 1 minute. So there has been a lot of work to rationalize this avalanche-like dynamics. That's why I entitled "Bridging the Gap Between Experiments and Theory." How far can we go in the understanding of this dynamics using the model I presented you? So there has been a lot of work, mainly actually from the experimental side, to find a proper system where you can measure the expected properties from the depending models. So I'm going to review some of them only, and also to highlight the limitation of the approach, of the theoretical approach. So how do you characterize the front evolution, the local spatio-temporal evolution of your front? So at each, this was the idea of Malloy, Stéphane Santucci, and co-workers. For each image, you record the front location, and then you plug in a matrix that corresponds to each pixel on each image, the time spent by the front, so in each pixel. So here there is 1 millisecond spent in each of these boxes, and then as you use many images corresponding to different times, you fill your matrix and you get a waiting time matrix telling you how much time the front spend in each position. And then you can threshold it, saying, okay, I keep only waiting time smaller than some threshold that is a few times the average waiting time. So in white, I have zone where the front has spent very less time. Okay? In other words, this zone here, the front has moved from this location to this one. So it defines me some clusters that you can define as avalanches. And the quantitative characterization of this cluster leads to power law statistic of this size, in particular Knut and then further students showed that they were power law distributed with an exponent close to 0.55. So in this experiment, they change the velocity, they vary the pixel size, they play with the threshold, and this is a robust properties.
These are the spatially connected clusters.
These are spatially connected clusters defined at the local scale. And so using the equation, you can, using the depinning equation presented before, now the fracture, the GC term in the equation, going to use a quench noise, meaning that in each point of your surface, you're going to take the fracture energy through a Gaussian distribution. And you have a disorder field of fracture energy, and you use this equation to simulate the propagation of the crack quasi-statically. And what you observe is a very intermittent dynamics where the crack front is pinned into some configuration, moved to another one through avalanches. And you have this characteristic spatiotemporal evolution in space only representing the time spent in each pixel by the front. The white region corresponds to zone where the front has visited very rapidly. You can also define pinning avalanches. Here, the white region are the region where the front has spent a lot of time, abnormally large amount of time, and you see lines corresponding to pin configuration. You can play the same game, analyze the statistics of the size of this cluster, so and actually rationalize the value found in the experiment with the non-local model.
On the right would be the black.
And from the right, you work on this map.
Distribution of the black.
No, it's a distribution of the white. Distribution of the white line, or the cluster of white lines.
Not a size. It's not an area.
It's he has some kind of. He has some small thickness, very small thickness, but yeah, it's more like elongated lines. Yeah. Okay, they calculate it also in experiments. It's pinning clusters, zone where the front spend a lot of time. So these are what you can extract. You can extract many things from this spatial map, but somehow the end of the story with that is you can go rather far with in the understanding of this intermittency using this model. It works pretty well until some limit. There are still open questions that maybe I discuss at the end.
Laura, may I ask you one question about this tau exporter? Are the avalanches which are connected and not?
Yes, exactly. These are connected avalanches. Maybe I can.
And it's not the area you were saying; it's the line.
It's
so
not
it's
the
even.
Okay, here it's. Okay, here it's obviously depending cluster area. You count the number of pixels. And you have an area of a zone where the front has moved very rapidly. That is in a vision of a front, you will have time t. At some time t plus delta t, your front will have moved forward. And it's with this definition of waiting time helps you to define this kind of cluster.
But I thought you just said on the other one you were using a line.
No, I'm not really using a line. I'm doing the same thing, and I'm going to count a pixel of white dots that are connected.
When they are not all connected together, the line.
No, they are not connected all together. No, you need.
Parts of the line may move while other parts are.
So it deconnect. Yeah. Okay.
Yeah, you see the values of C. You need. Okay, these are. To define this white line, you need to multiply the average waiting time by some constant, and here you need to go to very large values to actually, as you said, to not have only one single cluster. As you go to larger and larger, It's really a heuristical procedure that has been done in experiment, in simulation, and makes a reasonable job. Then I don't know if this exponent makes sense from
Spinning lasers are the one which stops.
Yeah.
The spinning the moves.
Yeah.
And do you have okay, because there is a scaling relation for the exponent tau if you consider the full class, the ensemble of all the avalanches that moves at the same time, no?
I go to that. I go to that, but that's true. We can make a first. Okay, I'll make this comment later. Okay. Okay, so now we're going to look at intermittency from the macroscopic scale and look at avalanches at the global scale. So the idea is to come back on the fracture process that is nothing but the transfer of mechanical energy into surface energy or fracture energy. So let's take this little sketch where you start from, I'm going to use dead load because it somehow makes the system perfectly isolated. I have a dead load that I'm going to let fall. It's going to pull on the material and let it fall as the crack propagates. So I'm loading my material with a constant force, and I have an isolated system, and the total energy through this process is constant. It's going to be composed of the mechanical energy, potential energy of the mass plus the elastic energy of the elastic solid, and surface energy. And the fracture process is the transfer of this mechanical energy, that is the potential energy of the mass at time t equals 0, to surface energy, so that at time t equals 0, I have an amount of mechanical energy. At time t end, I have no mechanical energy. All the energy into the fracture energy. Okay, I have this transfer. The whole question is how does this transfer take place? And it takes place on a very intermittent manner, as we will see. First of all, I need to define this quantity, the rate of energy transfer that we already actually somehow discussed previously. It's a variation. It's a power of energy dissipated in fracture or in surface energy. It's also the opposite of the rate of variation versus time of the mechanical energy. And this quantity we introduced it before because it's related to the energy release rate, G. So actually this definition is straightforward. Is G time delta EM is G time the surface crossed by my crack. So it's G time F dot time delta T time dZ integrated along the front. And the delta T, you get rid of the delta T. There is a B showing up from the definition of G. And you end up you can develop this term in two pieces and show that more or less the rate of energy transfer from mechanical to surface energy is proportional to the average crack growth. The constant is average fracture energy, the time the film, the specimen width. In other words, if you want to know the rate of transfer from mechanical to surface energy, you look at the velocity of your crack front, the average velocity of your crack front over Z. Vm is average along Z, not along time. This can vary with time. So this is a very practical way to look at the rate of transfer, and that actually will be the physical quantity in your problem.
Yeah, sure. This GC average is not the same which enters into the decimal.
It's in the equation you can write GC as a field, and a field of fracture energy that is the sum of your average fracture energy plus some fluctuation that depend on space, and this is this term exactly.
Can you
so this is an average over weak and tough regions, whereas your maximum force and maximum resistance is just the average over when the fracture is arrested, what you defined before, so what should be larger.
I'm not sure. You talk about this passage from ear to ear. I didn't explain it, but this you can develop. This term is G0 plus delta G, and G0 it's this simplification. Probably we can discuss it later. But this simplification arises from the development of G in terms zero order, first order. But this is spatially average fractal energy of your material.
Maybe discuss this.
Yeah.
We were just talking. Did you neglect the plastic deformation, or is it? I mean, away from them.
There is no. It's a very macroscopic view at the problem. I'm looking at energy conservation. So how the energy is dissipated during this process, I don't even see it. I'm looking at the mechanical energy of the whole system, that is an isolated system, how it goes into the surface energy, the fractal energy. I would say as long as what we discussed in the first slide work, you have a fractal energy proportional to surface, etc., this holds.
He has written it on the top. It's brittle fracture, not.
Yeah, but okay. In brittle fracture, you can allow some plasticity, localized at the tip.
You just have it localized.
You need the main hypothesis to use fractal mechanics is small scale yielding. Fracture process zone small compared to system size. Okay, so these are actually experimental data where you have the mechanical energy stored in your system as function of time as you go from this state to this one. So you go to some kind of 1 joule to 0 in terms of mechanical energy. You could plot the surface energy. Will be the same curve in the opposite way because the total energy is conserved. And the velocity that I represented here is the rate of energy transfer. You clearly see that when you have drop in the mechanical energy, you have large velocity. So if you want to have the rate, if you want to have the energy transferred from mechanical to surface over some time, you just integrate the velocity signal, okay? And you have a constant per factor, sure, but okay, that's the idea. That's why we want to focus on the average velocity of the crack. That gives a lot information about the avalanche defined from an energy perspective. Okay. So now, if you want to define an avalanche or the burst of energy you transfer from mechanical to surface, you need to integrate your velocity signal from one point to another, from the beginning of the avalanche to the end of the avalanche. That's what we do here. I mean, that's what classically you do, and that's Jonathan Varese, Daniel Bonamy have done in artificial rock. They have worked on a design heterogeneous material to measure these avalanches, and they have recorded the velocity signal as the one shown before, and defined as avalanches using a threshold. Okay, as usual, you never really goes to exact zero velocity, so you need to define a threshold, and you define avalanches as burst of transfer of energy, and you get the amount of energy transferred by just integrating this curve. Remember, V is the power of energy dissipated, so you integrate it over time, and you can look at the statistics then, statistics of size of avalanches defined in energy. From an energy point of view, and they observe power law statistics, an exponent close to 0.4 to 1.4. That is a bit that can be compared. That you can compare with the prediction of the depending model, that is slightly bigger. Okay, this also we can discuss. Different scenarios why it's slightly bigger, but the comparison is not completely stupid. No, I would like to make a comment on the values of the distribution of macroscopic avalanches, that is distributed with an exponent 1.4, and the distribution of local avalanches that were distributed with an exponent that is slightly larger. Okay. Actually, in this long range in this long-range elasticity problem, when I have one macroscopic avalanche, at the local scale I can have many small avalanches. These are the picture you will get at the local scale if you look at t and t plus dt, where v of t1, I will have a signal like this, t1 plus delta t. So during one avalanche, my front will have moved at different spots. So it means now if you look at the distribution in terms of energy of big avalanches, you observe something like 1.4 through the macroscopic measurement of this energy. And now if you look at the area, and here you have several areas, you see that big avalanches might be composed of several small ones. So instead of having one big avalanches, you will have many you will have many small ones. Okay, so you're going to feed this part of the curve, the big avalanches, with smaller ones. So you're going to break in pieces the small ones, the big ones, into multiple small ones, and you move like this to a slightly larger exponent. This is a qualitative scenario that might explain why you get an exponent slightly larger when you look at local avalanches compared to
bigger. But we talked about the fact that you can have quiescent periods even as part of a causal avalanche. So this one may also be too big in the sense that energy is seen as one event. That's part of something that's causal.
Let's take this example. If I do then this threshold here, I will have one block here and one block here. That might correspond to this one and these two ones. That's a good point. So also this 1.4, that might explain why this 1.4 is still slightly bigger with respect to the predicted value of. This is experiment here. Yeah.
The error bar on that
is probably order of 0.1. Yeah. Yeah.
So wouldn't these exponents then be dependent on the cutoff time or something?
Okay, as you see, they play a little on the cutoff. But it's not so much. Yeah. Exactly. That's a good point. If we lower the cutoff, problem you are never at sufficiently small driving velocity, so that you never really separate avalanches. They all take place a bit one after the other continuously. So if you have zero cutoff, then you have one big avalanche. You mix avalanches that are not, which should not be the same one. So you have a trade-off between low cutoff and large cutoff.
So this exponent will just get steeper, as Mark said. Okay. Even these ones where you think it's local, if you look close enough, maybe that's also smaller patches and things. There's no.
You have also the same. You're right. You can have the same threshold problem on the local avalanches. Yeah, that's a good point.
Are these data were acquired with optics or just seeing the different?
No. These are from a global measurement, macroscopic measurement of energy.
So then you have the disconnected regions together.
Yes, sure.
If you look at the species of avalanches, A1 and 2, can you see some pattern in the distances between the epicenters, let's say, for those?
No, this has
some structure, no?
I don't know if anyone looked at that. I don't think so.
This goes to the problem like in earthquakes where what's the difference between a foreshock, a main shock?
No, that's I think that's what we discussed last week. That's why I wanted to make a point also. That's exactly that. How do you separate aftershock, main shock, and probably a way to clarify all these points is to look at several quantities, not only the macroscopic avalanches are not the most probably the one who average a lot of things together, so probably not the most relevant quantity to distinguish between models. Or another, maybe a more efficient way is to look at the shape of avalanches. So I will not tell too much about it. Stefan will come at the conference to present this work. But you can now look at the, should switch on the light again, but, oh, I have a drawing here. You look at now the average shape of these avalanches. You average over many of them, and you normalize by their duration. So they have all the same duration, and you average out all these avalanches. You also normalize their amplitude. So they all collapse on the same curve with a lot of noise, and when you average these avalanches, the shape of these avalanches out, you find this shape. And in this work with Lorson, Mikko, Alava, and co-workers, they compare with the theoretical model with the long-range elasticity, and they found it was a reasonable agreement. The red and the black are other models, short range or other kind of elasticity. And they also, interestingly, they found also a scaling between the size, the duration of the avalanche versus the area, the size, the energy of one avalanche, with an exponent that is close to the one predicted by the deepening model. So at the global scale, the avalanche shape seems to give a closer result than the statistics of avalanche size for the deepening model. This has not been done so far in the experiment. We can also look at the local scale and the cluster, the average cluster shape. Now you ask, what is the typical size of this cluster? So here you have the slight asymmetry. It's really not obvious to see that it's. Karin, tell me if I'm right. It goes. It goes slower, and it starts slowly and finish more rapidly. That's it. The rate it's slightly.
Oh, if you have, I'm sorry.
The asymmetry of the avalanche in the long-range model is shifted toward the right.
You have inertia, you say?
No, there is no inertia here. With a long range, in this paper they claim that due to the long range elasticity, you have slight asymmetry toward the right part for the deepening model.
The mean field is a parabola.
No, it's not mean field here.
Yeah.
Okay, and here using the numerics, resolving the equation of evolution numerically, you also see that the average shape of the cluster is asymmetric. This is a propagation direction, so it's more extended backward than outward. So you have a kind of feeling how this avalanche can develop. They can start here, propagate spatially, and close up this way. The shape has not been compared with experiment, but the aspect ratio follows a scaling law that compare well with the experiment.
What is on the axis?
Is a front direction, propagation direction. Is a cluster in the dimensional
shape
space.
Of the cluster?
Yeah, it's the average shape of this cluster.
So what is the upper curves versus the lower ones?
The clusters have a kind of they have a shape. They have a potato shape, and this is the shape.
lower one is before the avalanche, and the upper is after.
No, look, I have areas. I have each cluster provide me an area with an upper limit and a lower limit. Propagation direction is this way.
So the upper limit is the upper curves?
Yes.
Lower limit is...
Yeah, sure.
How do you run x equal to?
Well, there are different procedures. I think we center this guy. Yeah, we center everything. We took the maximum and plug the. Okay, this is the zero. This is the middle. Yeah. We have a procedure like that where we pick up the middle of the cluster that we plug here.
In the average, you also pick up because you have avalanches like this. There is an angle, right?
Yeah.
You're picking.
No, we maintain the original shape and average them. We don't orient the
you don't rotate.
Yeah,
Okay.
we don't rotate them.
You know, there could be maybe a systematic, I don't know if it's an error, but from the front will propagate normally to itself. It won't propagate in a given direction. So if you take that into account, it could change the statistics.
Yeah, it might improve the average, yeah.
Improve or whatever.
So, Laurent, you would say that the depending model explains
No,
the model to interpret your results?
No, I'm going to the conclusion. I'm going to the conclusion. It's not so clear.
But A is the roughness
Yes, exactly. Yeah. It's this aspect ratio is defining the roughness of your clusters. Exactly. So I go to this point to the conclusion actually. So your question is, does the deepening-like model makes a good job at rationalizing all this experimental data? Okay, my first response is yes. They can capture many things. We discussed about the avalanche dynamics. It makes a rather good job to rationalize all this experimental observation up to the value of the exponent to some limit, but I would say it's a reasonable agreement. It's not on. There are also other interesting prediction of the deepening model that works well on the crack form problem. The roughness. Recently, people measure the roughness exponent, and they measure the 0.4 prediction that can be made from the model. You have also the average crack dynamics. So these 2 points, I didn't talk about it. You can actually measure the deepening transition. If you measure the velocity, your average velocity versus driving, you can have this so-called deepening transition where the velocity is going to go from 0 to a power law evolving. It's going to evolve as a power law of the distance to the critical threshold. So you can really explain a certain number of things, but you need to look at a fracture program under a very specific condition actually, that are not the general case. I've quoted two specific restrictions that makes that MIS model apply. Then you really need an infinite, very large system. This is due to the fact that if you want to have your kernel to elastic interaction remain the one we have set up, we need really to have avalanche size, front perturbation, characterized by a length scale that is much smaller than the sample size. And this is really a big restriction that has not been respected in many experiments in the 90s at the beginning, where it was difficult to rationalize observation, and that is still a big problem. A fracture takes place in finite size sample, and so if you want at least to compare prediction with experiments, you need particular to take specimen widths in this direction, very large with respect to avalanche size. That's really a key point. Another thing is then you need a scale separation between the material heterogeneity and the size at which all the dissipation takes place. This black box that we didn't talk about, this is assumed implicitly in all that it's very small with respect to a heterogeneity size. But in materials, dissipative processes take place at the microstructure scale, because it's where you have heterogeneity, it's where you have a mess, it's where you find a way to dissipate energy. So to have this scale separation, the best way I can think of is to build your own material where you artificially plug a sufficiently large length scale, a grain size, make of bead, glass bead, much larger than the natural length scale in your material. Or the idea of the heterogeneous adhesive, where we put artificially defect at a scale that is a millimeter scale, much larger than the scale of dissipation in this adhesive that are the micrometer scale. So I would say it's also a big restriction. And now I think the point is how we move forward from this model to more realistic situation. It's a very solid basis we can build from and extend this framework to broader cases.
This is very pretty, but if I took my glasses off, which I don't have right now, or something, and I said, okay, I have all this random pinning or something, but there's some mean that you talked about. And if I go and now increase the scale of the loading or something like that, so why can't I sweep this under the same rug that we call the dissipation and forget about it? Or if I can turn it around, I can think of a crack going through a homogeneous material. But then if I now put my glasses on and make them into a microscope, so there are always, a million defects in any perfect material. So I once again get to the limit where I have these pinning centers or something, but still fracture mechanics or continuum fracture mechanics works because it's a number or something. So how?
Okay, that's the key. Okay, the key response, but it can be debated by all of us. Is that the cutoff size of these avalanches, the maximum size of this fluctuation are bounded by the system size. Especially when we talk about brittle fracture, there is no length scale between the heterogeneity size and the system size. So that's why I have all these power law distributed objects. So the larger your system is, the larger the fluctuation will be. For some case, there is not always crackling and that. But when you have crackling, so it's not so. I mean, it's what. It's not easy to define a representative volume where you can put this fluctuation in and then smooth them out. I would say this is like the earthquake problem. The intermittency is macroscopic. It's not a correction. It's not a microscopic correction you can smooth out by taking a sufficiently large volume. We can. Yeah.
You're driving with this velocity, right?
Yeah.
So there is constant K. So this setting is scale. So what is K?
Oh, this setting, K is going to set a macroscopic length scale due to loading condition. And generally, it's a crack length, the total crack length or the specimen width. So this is your cutoff. So you have the maximum, it will set a maximum avalanche size. Okay, even simpler since some of you know well the equation of evolution. The length scale that is important is this one. This is 1 over length scale. This is provided by the loading. It's a length scale coming from the loading condition and the geometry. Typically the total crack length. This will set up a cutoff on your fluctuation. That might be of the size of your sample. That's why it's not so easy to neglect this fluctuation.
Have you measured some sort of dynamical exponent? Because you were talking about time series, maybe there are correlations between events, like we talked about last week with earthquakes. With the deep hitting model, there's really no correlation.
Okay, there has been people have people have measured the Omori's law in fracture. They have measured correlation in avalanche at a rather very short time scale, millisecond, and it's right now not so clear if we are talking about this type of effect when one avalanche can be composed of several avalanches. If we have viscoelastic effect of the type discussed by Alberto last week, open question.